We're surrounded by this kind of everyday magic. It's the thing that lets your car see the lines on the road or a store know what you picked up without ever going to a checkout. But here's the thing, it's not magic, it's computer vision. And today, we're going to pull back the curtain and see exactly how it all works.
I mean, really think about that for a second. You open up Instagram or Snapchat and boom, those puppy ears or sunglasses just snap right onto your face. How does it know where your face is? How does it follow your eyes, your smile, your nose, even when you're moving around? What's going on there?
And this very same technology is kind of quietly powering a revolution all around us. It's inside Amazon's Just Walk Out stores, letting you literally just grab your stuff and go. It's out on farms where these incredibly smart tractors can tell a weed from a crop, saving a ton on herbicides. It's the eyes for self-driving cars. And yeah, it's how your phone unlocks just by looking at you. All of this is connected by one single core technology.
And the answer to all of these little mysteries is a piece of software called OpenCV. It stands for Open Source Computer Vision. And really, it's the fundamental toolkit that gives developers and companies the power to teach machines how to see. Okay, so how does a computer actually see? Well, to get this, you have to completely forget what you think an image is. For a machine, it all starts with this one really simple but incredibly powerful idea. Let's just get one thing straight right off the bat. When a computer looks at a photo of, say, a cat, it does not see fur. It doesn't see whiskers or a cute little nose. It sees absolutely none of that. What it actually sees is just data. And that is the fundamental secret right there. Every single digital image you have ever seen in your entire life is, to a computer, just a giant grid of numbers. That's it, nothing more. Each of those numbers in the grid corresponds to one tiny, tiny dot in the image, what we all call a pixel. And the value of that specific number tells the computer everything it needs to know about that one little dot. And this table here breaks it down perfectly. So, for a simple black and white or grayscale image, it's just one grid of numbers. 0 means pure black, 255 means pure white, and everything in between is a shade of gray. For a color image, it's just 3 of those grids stacked on top of each other. One for red, one for green, and one for blue. You combine those 3 numbers and you can create every color you can imagine. All right, so pictures are just giant spreadsheets of numbers. Got it. But, knowing that is one thing. Actually doing something useful with it is where the real magic happens. And this is where OpenCV comes in. You can think of it as the ultimate toolkit for performing, mathematical surgery on those numbers. Seriously, think of OpenCV as the ultimate Swiss Army knife for images. It is packed, and I mean packed, with over 2,500 specialized tools or algorithms. Each one is designed to manipulate those grids of numbers in a very specific way to find patterns and pull out some kind of meaning. And some of the most basic tools are actually super intuitive. Like, if you want to make an image brighter, you just add 50 to every single number in the grid. Want to make it grayscale? You just average the 3 color grids into one. Blurring an image to get rid of some noise. That's just a fancy way of averaging a pixel's value with the numbers of its neighbors. See? It's all just math. And this is a brilliant example of how you can combine those simple tools to do something really complex, like finding the outline of an object. So first, you make a grayscale. 1 grid is way easier to work with than 3. Then you blur it just a little bit to smooth out any random, unimportant details. But here comes the crucial step. The algorithm scans that grid, looking for spots where 2 pixels right next to each other have a huge difference in their value, like a 20 right next to a 240. That signals a really sharp change in brightness, which is almost certainly an edge. Then you just connect those dots, and bam, you've got yourself an outline. So we have numbers, and we have the tools to find patterns in those numbers, like edges. But how in the world do we get from a simple outline of a flower to a car that can literally drive itself? Okay, let's connect the dots and see how these pixels become our reality. Let's start with a massive real-world impact. In farming, these precision spraying systems are an absolute game changer. Some farmers are reporting that they can cut their herbicide use by up to 90%. I mean, that is an incredible savings, both in money and for the environment. So how are they doing it? Well, they're running the exact process we just talked about. A camera on a tractor sees a grid of numbers. It uses edge detection to find the shape of a plant. Then, a machine learning model, which has been trained on thousands of examples, looks at that shape and says, yep, that's a crop.
Or, nope, that's a weed. Spray it. It's a direct line from pixel math to real-world action. And once you see it, you realize this same fundamental principle is absolutely everywhere. For those face filters, it's finding the edges and key points of your face to overlay the graphics. For checkout-free stores, it's tracking the outlines of the products you pick up. For self-driving cars, it's detecting the edges of lanes, road signs, and other cars. It's in security systems, and it's even in hospitals, helping doctors analyze the shapes and textures in medical scans.
But there is a catch, of course there is. OpenCV gives us this incredible box of tools, but the tools themselves aren't actually intelligent. They have to be taught what to look for. And that brings us to the single most critical component of all of modern computer vision.
This right here might be one of the most important sentences in all of artificial intelligence. It applies to every single computer vision system that exists. And it's something we really have to get our heads around.
Because here's the crucial point. These algorithms, they learn by example. To teach a machine to recognize a cat, you have to show it millions of pictures of cats that are labeled cat. But if your data is messy, or if it doesn't show enough variety, like cats in weird lighting or from different angles, your model is going to fail. You could have the best algorithm on planet Earth, and it cannot overcome bad data. It is and always will be garbage in, garbage out.
And so that leaves us with this big kind of provocative question for the future, right? We've done it. We've effectively given machines the sense of sight. We have the tools, we have the processing power. So the real challenge now, and honestly the biggest opportunity, is deciding what we should teach them. What problems do we want them to solve? What important patterns in the world do we want them to find? That is the next frontier.